And the reason is that in quantum mechanics you have the uncertainty principle that there is a possibility of creating pairs of particles in the vacuum. And they are a pair particle and an antiparticle where one drops in the black hole and the other one escapes. Normally, in empty space, they would reunite again and they just annihilate each other. But here, one drops in and the other one escapes, and you get radiation coming out. So this is the picture here. It's also where these two particles near the horizon, one escapes and one falls in. But if they're not on the horizon, then they can combine again. And this is going to be telling us something about the properties of this black hole, namely that it has a temperature, because its radiation is thermal radiation. And if we have a temperature and we have a mass and therefore an energy, we also have an entropy, and that entropy is a formula that Bekenstein already wrote down, namely that it's proportional to the area. So it has thermodynamic properties, precisely the quantities that I introduced as being emergent. The temperature and an entropy. And the entropy for a black hole is proportional to the area of its horizon. This was one of the more important discoveries, actually already 40 years ago they made this. And I think it is the first crack in Einstein's theory. Nothing is perfect, and actually that's one of my storylines, is that every theory eventually gets replaced by a better one, and you have to look at the right clues of where to look, and you find that the black hole entropy formula tells you something about what is the microscopic origin of gravity. By the way, I already said that Newton's law had something to do with areas. This area of the black hole horizon is the same area actually we're going to talk about. So there is an entropy formula that tells us how much information is contained in a black hole. And we're going to think about this information as bits. I told you information for me is bits. It's also can be measured by entropy because that tells us how many bits there are. And this is why this formula tells us how many bits we can associate with a black hole. Not ordinary bits, by the way. It's going to be quantum qubits a little later. So the information that is associated with black holes is not the information that we have classically on a computer. It's going to be the next computer. Actually, a black hole is the best computer you can have because you can store an enormous amount of information on it. Namely, the density here is the Planck scale. Try building a chip like that. This is where the limit is. This is how much information you can store on the surface. And it's, as I said, not ordinary bits, it's quantum information. And now let me explain a little bit more about what that is. I already said that bits are zeros and ones. Quantum bits, they are also zeros and ones, but you can also think about it as the spin of an electron, for instance. The spin of an electron can be either up or down, but it can also be something in the middle. And we call that a superposition. So it has to decide still whether it's up or down before I do a measurement. And this is why a qubit has many more possibilities. So a bit has only two possibilities, 0 and 1. A qubit can be thought of as a sphere. All points on this sphere is a different state of a qubit. And this is why if you do calculation with qubits, you're doing many calculations at the same time. Many more bits than we normally have in a classical computer. In a quantum calculation, you do all these things parallel. All calculations are being done at the same time. This is why quantum computers are much more powerful. More importantly, these qubits can be entangled. I already mentioned what that is, namely that if I measure two qubits, that the outcome is the same. This was discovered, let me do the calculation, it's like 80 years ago by, again, a familiar name, Einstein, together with two colleagues. Actually, you may wonder why Einstein does something with quantum mechanics, because he didn't like it. Well, this was also motivated to show that there's something very funny about quantum mechanics, namely that if you measure an object and you measure the spin here, it can determine the outcome of a measurement somewhere else instantaneously. He called this spooky action at a distance, and he said, this cannot be. This paper was not that important at the time, but in recent times, it's one of the most important papers because it's the first paper where they explained entanglement very clearly. And this is what makes entangled qubits. It's the power of quantum mechanics. It's the essence of quantum mechanics that we have entanglement. And our universe is very entangled. And so this is why this is the kind of information we're talking about. So it's a property of the quantum bits, and actually it's something that is already there before you start measuring it. It tells you that if you do a measurement here, that something else happens somewhere else. So this is already the qubits that I showed before. I mean, this is where indeed you have a 0 and a 0. If you do a measurement of this one, it can be either a 0 or a 1. So here, and the other one here, the other measure outcome might be a 1, but the outcome is always the same. So if I measure this one as a 0, then this one will be 0 as well. And if it's a 1, the other one is 1. But a priori, there's 50-50 probability when I do the measurement. So this is called entanglement. And I'm going to denote this by this picture of a sphere by connecting a little line between it. So entanglement is like a connection between two of those qubits. So I'm connecting qubits together, and this is the way I'm going to build space-time. So this is going to be my microscopic picture of the molecules of space-time. So this is what Bekenstein and Hawking calculated. They calculated that there was an entropy associated to horizons, and this has to do precisely with this pair creation, because here we are creating a pair of entangled particles, and they describe the amount of information. So the entangled qubits is really what's being counted by this formula. So this is the answer. So what is this entropy counting? It's entangled qubits. And they are the building blocks of space-time. And they are measured by the area. But I'm going to say it's the other way around. Actually, the amount of qubits is going to determine the geometry, and it's going to determine the area. So the geometry of Einstein is going to be derived from this language. So this is as far as I want to go, at least, explaining the ideas. This is a current state-of-the-art kind of development going on in theoretical physics. Thinking about gravity in terms of quantum information and deriving its laws just the same way as we derive the laws of thermodynamics. And that's called emergent gravity. And this is where I want to connect now, final slides, to the dark universe. So this is a slide summary. Space-time and gravity are emergent, and this is actually a lesson we learn not from just black hole physics. I didn't tell you about string theory because I have only that many minutes to talk, but string theory itself also actually hints in the same direction. A lot of what we're learning nowadays comes from studies in string theory where we also see that this emergence of gravity from quantum information is very natural. This is all theoretical physics. And you might say, well, why are we doing it? Are we learning anything new? And in particular, is there an observational evidence? So one thing that I have to mention is that we have to rederive first the laws that we already know from this idea. This can be done. And I wrote a paper already about 7 years ago, a little more, which was called On the Origin of Gravity and the Laws of Newton, because that's one of the laws you want to derive. And what I showed here in this paper, that indeed if you assume that the amount of information, this entanglement, is proportional to the area, that's an assumption, by the way, then you can derive Newton's law. Just by using the same tricks that we use to derive thermodynamics. So there is Newton's law. And here's this picture of the information stored on a surface, and we find indeed the 1/r² R² law because the area, it grows like the area. This, by the way, as I said, is an assumption, and you may wonder whether this assumption is true. And this is where the possibilities are maybe to explain what's going on here. So now I'm going back to my original question. Is there some way that something strange or different happens in this galaxy? I already told you that the observations tell us that something different happens, but can we also explain this theoretically? Indeed, I'm going to say there are different laws acting here, because the laws that we have currently derived, Einstein's equations, are derived from observations that we have done in the previous century, colliding black holes, lots of stuff. But if you think about this question here, how long have we been observing the universe? If you think about the history of the Earth, actually this was from a slide actually from the internet. I could have put the universe here. The history of the universe, if we would take that to be 1 year, then humans only arrived 1 minute before midnight on the 31st of December. And how long have we been doing science? Fraction of a second. It's like taking a snapshot of the history of the universe and then drawing conclusion about its entire history. I showed you this experiment. The snapshot was the bounce. What happens to the universe is this, and there's a lot of dark matter in here because it's created an enormous dent. If I would apply my theory of elasticity to this, I would have drawn the wrong conclusions. So if the universe has this kind of slow dynamics happening at very large scales, we can explain these phenomena. And now let me go back to the picture here about what we don't know about the universe. This is what we have used. And let me ask you the question, according to current theory, where is all the information sitting? In this picture. Any idea? That little tiny yellow stuff. It's the photons in the CMB. That carries most of the information according to current theory. I think that's wrong. All of the information is contained there. Most of the information. And then we have a totally different way of thinking about it. We're missing most of the entropy. This number is 10 to the 90. That's the number of bits you would need to describe the photons. This number, I claim, is 10 to the 120 because that's the size of the horizon of our universe if we would have only dark energy. So this is going to be the conclusion. I'm going to think about our universe as if we are living inside a giant black hole which has a horizon, except we are not outside the black hole, we're inside. Why do we can think about the universe as a black hole with a horizon is because of the following fact. We know, according to Hubble, that things move away from us with faster velocity when we go further distances. So objects further away move further with higher velocity. So this is Hubble's law. The velocity is proportional to the constant of Hubble, times the distance. So there is a distance when this would become the speed of light. And things that are moving faster than the speed of light we cannot see. So there's a furthest distance we can see, and therefore we have a horizon, which distance is given by, well, you take the velocity to be c, and you divide by h, so this is the distance to the horizon. If we would be in a universe which is constantly just expanding according to the Hubble law. This tells us then the size of the horizon, the size of the universe, and actually also the size of the number of bits I need, namely it's going to be the size of this horizon, again, measured in Planckian units. I'm going to claim this is information associated not to the horizon itself, but to the dark energy. There's an observational fact. Well, maybe I should tell you the picture first. So I'm going to explain what happens in galaxies' rotation curves. Namely, there's information contained in the dark energy. The matter actually pushes it away. It's like elasticity pushing it away. It creates a hole in it, but entropy wants to move back. It sort of wants to increase. It pushes back. I've done a calculation. If you don't believe me, I should take this aside because all the equations are on the blackboard. These are the equations of a paper I wrote about a year ago that does a calculation where at the end of it, I'm going to explain the data that are here. And let me already tell you a curious fact that should be been a smoking gun for why this is the right explanation. If you look at this curve here, so this is what Newton would have predicted, and this is what we observe. Turns out that the deviation always happens at a very particular gravitational acceleration, independent of the size of the galaxy. If you calculate or measure, I should say, that acceleration, turns out it's related to the Hubble parameter, which is very mysterious because a galaxy is a very tiny object, so what would that relation be? I explained that in that paper, and the formulas are like here. So I use entropy, the temperature, entanglement. Eventually, a formula comes out that describes this behavior and precisely the flattening of these rotation curves with this velocity of acceleration in there. So these ideas are connected to observations, and I think this is proof that quantum entanglement is the origin of gravity.